Welcome back to Honors Calculus. In this video, we are going to finish our discussion on differentials by taking a complete tangent to think about summation notation. Summation notation has absolutely nothing whatsoever to do with differentials, but it's a small idea that's going to be vital to us as we move forward into the next couple of lessons. There are a lot of rules here, but this is one place where I give myself the luxury of not proving the rules, because the rules have nothing to do with calculus on their own. Calculus makes use of them, but they themselves are not calculus. For anyone who is moving onward to a course in discrete mathematics or number theory, you will see the proofs of these ideas in one of those classes. For the rest of you, we can just start looking at some of these and play around a little bit with the properties and see what we can do with them. But summation notation uses the Greek letter capital sigma. And it uses a sequence of subscripts. Subscripted ideas like this are functions, but instead of being a function of a real variable, we generally assume that this to be a function of a discrete variable, like an integer. So in this case, we're taking the sum, k goes from 1 to n of a sub k. What that's telling us to do is calculate a1 plus a2 plus, and keep going until we get to an. Evaluate the first n values of this sequence and add them all together. Generally, a situation like this is going to give us an explicit formula to work with. So we might see something like the sum k goes from 1 to 5 of 2k minus 3. Right, so we have, when we evaluate this, 2 times 1 minus 3 plus 2 times 2 minus 3 plus 2 times 3 minus 3 plus 2 times 4 minus 3 plus 2 times 5 minus 3. 2 times 1 is 2, 2 minus 3 is negative 1. 2 times 2 is 4, 4 minus 3 is 1. 6 minus 3 is 3, 8 minus 3 is 5, and 10 minus 3 is 7. Adding that up, we end up with 15 as the value of this summation. For small numbers, this works perfectly fine. There's nothing wrong with it. We can keep going without any issue. We're not only going to be dealing with small numbers, though, so we're going to need a couple of basic rules. The first rule is the rule of linearity. If I have some constants, C1 and C2, that are being multiplied by some sequences, AK and BK, I can split them up the same way I split up the derivative or the limit. So we'll have C1 times the sum, K goes from 1 to n, of AK, plus C2 times the sum, K goes from 1 to n of BK. Essentially what we're doing here is distributing. We're using the distributive rule of addition and the associative property of addition in order to clean up our mess a little bit. And if we combine that with the power rules, then we'll be able to evaluate sums pretty quickly. The zero power rule, the sum k goes from 1 to n of 1 is equal to n. That makes sense. If you add 1 to itself n times, you end up at n. The others do not quite make sense. Like I said, if you continue onward in further mathematics, discrete mathematics is a place where I prove all of these, or I ask my students to prove many of them themselves. If you take the sum of k goes from 1 to n of k, you end up with n times n plus 1 all over 2, which is an obvious property, I'm sure. If you take the sum, k goes from 1 to n of k squared, you get n times n plus 1 times 2n plus 1 all over 6. And if you take the sum, k goes from 1 to n of k cubed, you get n squared times n plus 1 squared all over 4. And with these 4 power rules, along with the linearity, we will be able to evaluate some rather large summations. For example, I'm going to run out of space on this page. Let's go to a completely clean slide to prove this one. For example, if I want to take the sum of k goes from 1 to 100 of k squared minus 2k all over 5. I can split this fraction up as 1/5 k squared minus 2/5 k, then use the property of linearity to separate this and call it 1/5 times the sum, k goes from 1 to 100 of k squared, minus 2/5 times the sum, k goes from 1 to 100 of k. Now, using the power rules, the sum on k squared is n times n plus 1 times 2n plus 1 all over 6. And the sum on k is n times n plus 1 all over 2. And I can grab my calculator and calculate 100 times 101 times 201 divided by 5 and divided by 6 comes out at 67,670. Then I can take 2 times 100 times 101, divide by 5 and divide by 2. I'm sure I could have simplified that, but that's good enough. I get 2020. And subtracting these things gives me 65,650. So by using the properties of the summation, we can calculate this quite a bit faster. Right. Following the same procedure using the properties of exponents, I would like you to calculate the sum. K goes from 1 to 75 of k squared minus 3k plus 5. Take a few minutes, see what you can do with that one, and I'll see you in the next video.